All right. So once again, the first thing I'm going to do is isolate the trig function. So I'm going to add 3 to both sides. 4 sine x equals 3. Divide both sides by 4. Sine x is equal to 3/4. All right, that's a positive number. So now when I look at my quadrants, I'm looking for the quadrants where sine is positive. You'll notice I kind of know ahead of time there are going to be 2 of those. Okay. So sine is positive in quadrant 1, so I'm going to have a solution here. And sine is positive in quadrant 2, so I'll have a solution here. Okay. The reference angle in this quadrant will actually just be the solution that I get in this quadrant, because here my solution is an acute angle. Okay. So here I'm just looking for x. Here I'd be looking for x equaling pi minus alpha. Okay. Now, 3/4. Now that does show up in a special triangle. If I have an angle theta whose sine, actually no it doesn't, never mind. I was thinking of the 3, 4, 5 triangle, which is one of those special triangles that has integer sides. But the biggest side has to be the hypotenuse, which is 5, and it's not. The hypotenuse here would be 4. Okay. And even though that's kind of a special triangle, it's not a 30, 60, 90 or a 45, 45, 90. The sides are special. I don't know what the angles are other than describing them in terms of inverse trig. So I'm going to say, okay, looking at this x right here, it's the acute angle whose sine is 3/4. X is just going to be arcsine of 3/4. And that alpha is also going to be arcsine of 3/4. So x here would be pi minus arcsine of 3/4. So these would be my 2 solutions in the interval from 0 to 2 pi. If I wanted to get all solutions, all I'm going to do is add a multiple of 2 pi to each of those. So I would get arcsine of 3/4 plus 2 pi n, and then pi minus arcsine of 3/4 plus 2 pi n, in both cases where n is an integer. Excellent. Okay. Why don't I just take a look at an example that involves tangent while we're at it? And then we'll start taking a look at some slightly more complicated things. So let's say I have 3 tangent of x plus 1 equals 5. Okay. So it doesn't always have to be set equal to 0. It can be set equal to whatever number I want. Okay. So take a moment, pause the video, try this one on your own, tune back in, and we'll work through it together. Welcome back. So I'm going to isolate tangent. I'm going to subtract 1 from both sides, so I get 3 tangent of x is equal to 4. I'm going to divide both sides by 3, so tangent of x is equal to 4/3. I should probably mention, when we were solving for sine and cosines, I did make sure that there were solutions to all of those things. Sine and cosine, remember, can only take on values between -1 and 1. So if you ever get an equation, like if this were sine and I said sine x equals 4/3, I'd say, no, it doesn't, that's too big. That would actually be an easy problem. I'd just say no solution. But tangent can take on all real values, so there are going to be some solutions. Okay. So if I'm looking for solutions between 0 and 2 pi, I can do exactly what I did previously. I can think in terms of quadrants. What are the 2 quadrants where tangent is positive? Well, tangent's going to be positive in quadrant 1, so I'm going to have an angle x here. And then tangent's negative in 2, but it's positive in 3, so I'm going to have an angle x here with a reference angle alpha. And there won't be a solution in quadrant 4 because tangent is negative there. Okay. Now, again, because this is an acute angle whose tangent is 4/3, and I recognize 4/3 is not something I'm going to get in my 30, 60, 90 or my 45, 45, 90. So this is just going to be arctan of 4/3. This is going to be pi plus arctan of 4/3. So my two solutions between 0 and 2 pi would be arctan 4/3 and pi plus arctan of 4/3. Now, one thing that's kind of special about tangent is that if I drew in my other solution here, that's just pi more than x. When I've got solutions in diagonally opposite quadrants like this, they're pi apart. In degrees, it would be 180 degrees apart. Okay. Now, that's reflected in the fact that the period of tangent and cotangent is pi. So I know if sine of this angle is 4/3, if I add pi to it, I'm going to hit the next time when my angle is 4/3. What's happening is that was this point right here in this period of tangent. But in the next period of tangent, we just repeat those values, and this point is going to be exactly pi apart because that's the period of my graph. So when I'm finding all solutions, I could say this one plus 2 pi n or that one plus 2 pi n, but I can actually consolidate and I can just say arctan of 4/3 plus pi n, where n is an integer. Notice if pi is 1, I'm going to get pi plus arctan of 4, not if pi is 1, if n is 1, pi is not 1. If n is 1, I'm going to get pi plus arctan of 4/3. If n is 2, I'll get x plus 2 pi. I'll get an angle that's coterminal with that. So with tangent and cotangent, that gives me a nice way of sort of consolidating my answers. I will generally write the solutions this way, and you can expect the back of the book probably will too. I would accept it if you wrote this plus 2 pi n or this plus 2 pi n, because that is equivalent, but it's slightly preferable if you can get in the habit of consolidating and writing things in as concise form as possible.